Alrighty, I am back and let me make sure everything is working. I just finished the previous stream and I am starting a new stream. What are the odds? Alright, so let's see here. Alright, I want to make sure my audio is coming through properly. Yeah, looks like it's coming through good. Alright, so let's get right to it then. As you can see, I have a different setup now. What happened was I streamed about 20 hours worth, close to that, and on StreamYard. And I was streaming at 720p. I switched over to Open Broadcasting System, OBS. I've used it before. I just was a little lazy to set it up, and StreamYard was free, but now I'd have to pay $180 to keep using it. So I'm like, I'll just do OBS. Anyway, so yeah, I'm pretty happy with it. We are going into 2.2. It's going to be a little different, though. I'm not going to immediately start answering questions. Rather, I'm going to read the chapter, and then we are going to proceed. That's because this is getting more into proofy stuff. So it's just like, I have to... this is like some very important knowledge for us that... Okay, so yeah, here we go. Alright, so we're going to read 2.2. The word "and" can be used to combine two statements to form a new statement. Consider, for example, the following sentence. R sub 1, such that the number 2 is even and number 3 is odd. We recognize this as a true statement based on our great understanding of the meaning of the word "and." Notice that R sub 1 is made up of two simpler statements. P, such that the number 2 is even, Q, such that the number 3 is odd. These are joined by the word "and" to form the more complex statement of R sub 1. The statement R sub 1 asserts that P and Q are both true. Since both P and Q are in fact true, the statement R sub 1 is also true. So yeah, if you have both truths, this is, we're going to draw a truth table real quick here. So, this is how you do this. Say P, Q, P, and Q. Okay, this is a basic truth table. So we're going to say true, true, false, false. And then we're going to alternate in half. True, false, true, false. Okay? So now, if P is true, so let's just take this first statement. So let's see here. P, such that... You don't have to say such that, because at this point I'm just writing in English, so we don't have to use math lexicon. P states the number number 2 is even. Q states the number 2, I'm sorry, number 3 is odd. Okay? So now, if we say, if the first statement P is true and Q is true, then P and Q are both true. So there's no disagreements. The truth carries over. Okay. Now, but let me just refresh this because the screen's kind of weird. It doesn't seem to be. Maybe I have to hit play. That's why. Okay, so that's what's going on. Turn off the volume. So anyway, yeah, basically this is a truth table, and with the truth tables, what's happening is that P is true, Q is true, the 2 and 3 is true. If P is true and Q is false, then it is false because the rotten apple spoils the bunch, basically. So Q is rotten, the rot spreads to P. If P is false and Q is true, together they are false. And if one is false and the other is false, well, they're both false. So in this case, two falses don't make a truth. We'll see that under certain conditions, it's a little different. The truth tables are a very complicated thing. There's There's many. There's P, Q, and we can have R, for instance. And there's nots and ors. There's all kinds of really cool stuff. So we're going to do a lot of truth tables, and we're just going to work through a couple on this. Right here, this is and. All right, this is very important. This is why I was like, okay, I can't just blow through this. I have to explain some of this because, and you really should be reading, if you're watching this video and you're trying to learn something, at least read the chapter. It's only like 1 or 2 pages long. Get the book. The book's free. It's in the video description. Just download it. I have a physical copy. The physical copy is really nice. So yeah, get the book. Anyway. It's part of the Creative Commons. That's all I'm saying. Now, we continue here. Okay, so here we go. From these, we can see. All right, so then we're going to continue. Now, we're going to look at this. Or. So I'm moving my coffee off the table here so I have a better reach. P, Q, P, or Q. So in terms of and or, and, or. Okay, it's kind of how you could remember it. The or doesn't really work, but if you know the and, then the other one's the or. Okay, that's kind of how you remember this. All right. So the first one just gets all, we go true, true, false, false. So you can technically put, you can go false, false, true, true, or true, false, true, false. But the thing is, it's easy to organize it this way. Next one just gets half as much. Half of the half. So we're going to true, false, false. So now we're going to establish if they're true, then they are both true. Okay? If P is true, but Q is false, it's still true because only one has to be true. If P is true, is false, if P is false, but Q is true, the statement overall still holds. We only need, our apples are separated into 2 bowls. Okay, we just need one of the bowls not to be rotten. But if both of the bowls are rotten, if both are false, sorry, it's all false. Okay, so this is our truth tables for ands and ors. Okay. By the way, there's also an exclusive or. I don't know if we covered this yet. Right. It is important to be aware that the meaning of or expressed in the above table differs from the way it is often used in everyday conversation. For example, suppose a university official makes the following threat: you pay your tuition or you will be withdrawn from the school. So the understanding is, hang on, you understand that this means that either you pay your tuition or you will be withdrawn from the school, but not both. So in mathematics, we never use the word or in such a sense. For us, or means exactly what is stated in the table for or. Thus, P or Q being true means one or both of P and Q is true. If we ever need to express the fact that it's exactly one of P and Q is true, we use the following constructions. So exactly one but not two. P or Q but not both. That's an exclusive or. So remember what we said. You either pay your tuition or you get kicked out of school, but you're not going to pay your tuition and get kicked out of school. And in this case, for us, but the or here, when we say, is we can have both outcomes. It's not an exclusive or. So generally, an or can function like an and in mathematics. Just look at the truth table. If P is true, if you paid your tuition in P, and then you also got kicked out of the school, it's true. So I know it's a little mind melty, but trust me, just roll with it. Mathematics and English lexicon are a little different. In some ways, a lot different, but All right. I'm starting to lose my voice. I have like a I don't know, like by 11 or 12, I start to get gravelly. That's why I was doing the stream yesterday. I had to stop it because I was just like hacking and coughing. It was a terrible, terrible sound. But you're getting a much better result. I'm taking a longer time with this. And you're going to see that we're not going to be able to blaze through these chapters as quick as able to because it's very dense material. And especially when we get to proofs, we're just going to slam on the brakes. It is going to be very, very slow going because we have to write whole paragraphs explaining it. Anyway. All right. Remember, I am just a landscaper. I am a math student, also a computer science student, and this is a class I did not pass, so I'm studying up to retake it. And basically, that's it. If I get something wrong, just don't go citing me to your professors. All right. But anyway, getting back to what we're saying here, we could say either P or Q, and exactly one of P or Q. Exactly one, but not both. Either P or Q, but not both. P or Q, but not both. You see how that works? Those are exclusive ors. Now, and this is more like when you have to write up. When you write a sentence is not the same as when you write mathematic. Although oftentimes when we have to write something mathy in a sentence and we want to be very precise, we can switch to logic and just write it like this. If the university official were a mathematician, he might have qualified his statement in one of the following ways. Pay your tuition or you will be withdrawn from the school, but not both. That's awesome. That's really cool. Pay your tuition or you will be withdrawn from school, but not both. Either you pay your tuition or you will be withdrawn from school. Okay, that's more acceptable. All right, to conclude this section, we must mention another way of obtaining new statements from old ones. Given any statement P, we can form the new statement, it is not true that P. This is called a not. For example, consider the following statement. The number 2 is even, okay? All right, so now that's our statement. For example, stating the false statement, 2 is a member of the empty set. We get the true statement. So we're gonna say 2 is a member of the empty set, which is false. So we're gonna say P. And this is false. If we say not P, it makes it true. Okay? So basically that's what they're trying to say there. The truth table for P and not P. P, not, by the way, the not is not just for P. It could be not Q, not R. It could be not P and Q, not P or Q. We'll see a lot of different ones. We could have like 8 rows of different truth tables, or like in other words, like each column it would have like not 8 rows, but well, actually, yeah, for each column you get an additional row. But anyway, notice here we go. We have if P is true, Q is false. If P is false, not P is true. Okay, pretty simple stuff. So this is almost like you could think of in terms of A and the component of A, right? There's no overlap. It's either one or the other, but you can't have both. And not P. One of the cool things in mathematics is one of the easiest ways to prove something is if it's something very simple, and by simple I mean simple to prove, you can just do a direct proof, just like show an example. Or if it's something a little harder, you can try to prove the opposite. So proof by contradiction. Anyway, there's many different skills and proofs that we got. So anyway, getting back to this, the statement not P is called the negation of P, okay? The negation of a specific statement can be expressed in numerous ways. Consider P such that the number 2 is even. So here's a couple of ways of expressing a negation. Not P. It's not true that number 2 is even, not P, such that it is false that the number 2 is even, not P means the number 2 is not even. These are true statements because they're not P. And we're taking P and we're saying, nope, not P. And we're saying, no, it's not true that 2 is even. You see how that works? P states the number 2 is even, and we're saying, nope, we don't agree with that, not P. It is not true that 2 is even, for example. Now, okay, so just to be clear, the number 2 is even, and not P is a false statement. So just to be, again, this is, but it's just an example in our truth tables right here. Again, whether something is P or not P, whether it's true or false, P can be true, then not P is false. Not P can be true, then P is false. Just keep that in mind. And P is just another letter. You know how we had sets? P is just an assignment. Think of it as a set of a sentence. It's a sentence set, but not like distinct, each letter broken up. It simply means that it refers to a statement. This is how truth works. Truth tables and logic, where you assign a statement to a character like P or Q, and then you can roll with them and twist them around and move them around, and you can establish various truth tables and see, well, where are they going to work and what will be the results. When you have multiple moving parts like P, Q, and R, and P and Q, P or not Q, and not P or Q, so like that. So it gets complicated, but truth tables will help get us through it. All right, now, in this section, we've learned how to combine or modify statements with the operations and, or, and not. Of course, we can apply these operations to open sentences or a mixture of open sentences and statements. For example, X is an even integer and 3 is an odd integer is an open sentence. That is a combination of an open sentence and a statement. So if you have an open sentence, again, remember that rot idea? You know, the rotten apple spoils the lot. If you have a statement is not an open sentence because a statement has a truth value to it. An open sentence does not have a truth value to it. But if you combine the two, the fact that the open statement is attached, the open sentence is attached to a statement makes the whole thing an open sentence. So that just keep that in mind. All right. Okay, let's just do some, here we go. All right, and we're going to go to the next page. I'm going to start doing some equations here. Okay, there we go. Right. Okay. So we have and say Q, P. So so in this case, we're going to say that be sure to state exactly what statements P and Q stand for and express each statement or open sentence in one of the forms, P and Q. So we're going to say this is P and Q. And this is what I'm saying they stand for. Okay. So my answer to this is P and Q. Okay. Just going to do one more and then I'm going to check the answers. X is not equal to Y. So we're going to say, let's try not P. Whereas not such that, think about how to write this. Just give me a second. I gotta think this through. Not P. Let's see here. I want to know. And P is equal to X equal to Y. Something like that, maybe. Not P. Or we can say such that P. Maybe equals is the wrong term. We usually give it an assignment. Either a member of, or we're going to say like this. All right, let's try and see what these two, how I did here. All right, bear in mind, I am a student. I do make mistakes. I make a lot of mistakes, but that's okay. That's how we learn. All right. P and Q for the first one is even. Q8 is a power of 2. So you want to rewrite them a little bit. I didn't rewrite them, so we're just going to rewrite this. P. Okay. 8 is even. Q8 is a power of 2. Okay, so that's what. So I put them in the right places, but I didn't rewrite them. So I probably would have gotten full credit for this. Yeah, I would think. Let's see here. Okay. So the way they did this one, did a little differently. They said not X is equal to Y. So what we're trying to do, okay, so I made a mistake on mine, and I'm going to explain what the mistake was in a minute. But basically, we are trying to recreate this statement in logic. So X is not equal to Y. We want a not in there somewhere. So the not, we're going to take it and put it right there. We're pulling it out. So that leaves X is equal to Y, and the not is on the outside. So you could also write this, not P, and they're saying where P is equal to, such that X equals to Y, okay? So in other words, again, we want not P, not, so X is not equal to Y, and that's, we're recreating the exact thing. We're not trying to contradict the contradiction, which is what I did, right? This is where I made the mistake. I tried to say, well, no, I kind of did a double negative there, essentially. Okay, but that's been fixed now. There. 5. Okay, so I'm losing my voice a little bit. It's getting late. Like I said, if I talk too long, with too late, I start to get a little gravelly. All right, let's see. Y is greater than or equal to X. I'm gonna think about this. P, Y is greater than X, Q, Y is equal to X, P, and Q. That's how I see it. We are trying to recreate that statement. All right. Let's see here. So, oh, wait a minute. It wouldn't be and. Actually, this is and. Oh, okay. I'm sorry. I was wrong about that. Well, there's a couple of ways. Let's do it this way. P or Q, because P it can't be both at the same time, right? If X is 3, Y can be 3, then it's equal to X, but it wouldn't be greater than X. If Y is 4, it would be greater than X, but it wouldn't be equal to X. So I would say P or Q. But that's not what the book had. I'm just saying that would logically make sense, at least in my head. So this is the one I would stand by. The way they did it, here's another way. And again, keep in mind that you can write logic in a number of different ways. There's a number of different ways you can structure it and whatnot. So we're gonna look at what they're doing is we can say not y is less than x. It's a little less intuitive if you think about it. Like normally, if you, like I said, if you want to recreate it, you look at what you have there and you just recreate it. Now this is like they're like, okay, so you have really 3 options, 3 ways this can go. Y can, let's say y is 4, right? It can be greater than x. So if x is less than 4, then say x is 3, then y is greater than x. If x is 4, it's equal to x. If x is 5, it's less than x. So there's only 3 potential outcomes, right? So now what we're going to do is we're going to say not the outcome that it's not. So our statement, we're saying that is the true statement, and we want to recreate it. And the way we're going to recreate it, we're going to say not the statement that it's not. It's a double negative creates a positive. What I did here is I said that, and also we can do this. Here's another way we can, this has it. Not P where P such that y is less than x. Okay. Forms of, now in terms of like whether my answer would hold, even though it's different from the book, we are allowed to use it in the form of P and Q, P or Q, or not P. So in this case, I should have gotten full credit. Again, it doesn't make my answer wrong and theirs right. Their answer is correct, obviously, but I would say my answer is correct also because it gets the same result. When you're writing logic, you just can write it in different ways. It's fine. But generally, they'll kind of come out the same way. You'll see that. Okay, that's 5. Let's go to 7. Okay. All right, we're going to go to 7. Okay, so the number x equals 0, but the y does not, okay? Okay, so, well, let's assign it. P such that x equals to 0. Q such that y does not equal to 0. Okay? All right, so the number x, but the number y does not. So we're going to say, let me think here. Can we go P and not Q? We can do that. P. This is a little more advanced. It's not one of the forms they're giving us, but I'm just going to put it down here. It's just a little more convenient. And I'll see if I can come up with another form that's simpler. P and not Q. So we're going to say P such that X equals to 0 and Q, Y equals to 0. P and not Q. The number X equals to 0. P states over here, X equals to 0. Yes? Good. Not Q. Q states Y equals to 0. Not that. So then it does not equal to 0. So basically that's how I'm going about it. Now let me think here. If I did this any other way, well, my divisions of P and Q, I generally agree with them there. We can say P and Q were let me see here. We could also go P and Q, I guess. We can go up here, P and Q. And then that way, since we specify what P is, what Q is, and even though they mean opposite things, together they work. P is X equals 0. Q is Y is not equal to 0. Both statements are true. All right, let's take a look, see what the book says. Okay. All right. Oh-ho! Heyo! I got it. I got it. Your boy's a wizard. You're a wizard, Harry. Haha, nice. So yeah, again, when you do logic, I haven't done a lot of logic, I gotta be honest. But that just felt like the more natural way to do it. So because that way I took the not, this not, and then I moved it up there. Basically, that's the only real difference. The statements are the same, okay? You know, it's just like, this is just more neater. But that's what the book said, and yeah, it's more neater to put it this way. I can take this and put it right there, and then it'll be the not. But we don't want to do that because it looks nice the way it is. There's a certain, I don't know how to put this. There's a certain elegance to doing certain things a certain way, where it's like, it just feels right. And it's not that it can't be written any other way. It's just like certain forms and structures, the organization of it just makes sense. You know what I'm saying? Anyway, it is what it is. All right. Let's go to the next one. All right. Anyway. Okay. X contains A minus B. Now, X is a member of A minus B. Okay, so X is not a member of B. So let's say this. P. X is a member of A and Q. X is not a member of B. X, let's say it that way, and we're going to say not. P and not Q. Both statements have to be true. X has to be a member of A, but it cannot be a member of B. If B overlaps A, it should take it out. The question then becomes, yeah, I think this is the P and not Q. I think this would make sense. The only question is, there's going to be a conflict of logic here. Let me think what else we can do with this. Yeah, let me just think here. I'm just checking the health of my stream here, make sure everything's running. All right. Yeah, it seems to be up and running. Okay. I gotta think here. I gotta really think. So, how else can we do this? X is a member of... Let's see here. P or Q. What if you did or? But no, there's a subtraction. You know, I think this is the way to do it. I could be wrong. Let's find out. Yep, that's what they wrote. They wrote it a little differently, but it's just that I put assignments. They did not use assignments. The reason they do this is they want us to be able to read and be comfortable with different forms where we encounter them. So we can do this also. We could write X contains A and not X is not a member of B. So notice, it's the same thing. If we put the P and I fill it in here, put that there, it writes exactly the same way. So what I wrote and what they wrote is identical. It's just they used a different form. Normally, I mean, I don't know about normal, but essentially, I would probably just do a definition, what P is, what Q is, and then I would write it P and not Q. Versus writing, I mean, like for simple stuff, I guess it doesn't really matter. But if it gets like long and I have to do like, you know, various, you know, iterations of logic or something like that, it can just become confusing. You know, you've seen me before where I just assign something. I'm like, okay, this is too big. I don't want to deal with it. I'm just going to assign it to a character. Like I assigned what A, and we know the operations to do on A and B, the result thing set. I'm going to call it C, and then I perform the operations on C. So, you know, like, it's convenience. But you have to know what it is that you're doing and where to pull it out. Anyway, just keep that in mind. But this is relatively simple stuff we're doing here. Okay. 11. A contains... See, it really is helpful to read the chapter. I mean, obviously, this is the kind of material you have to learn it somewhere, but reading is a big way to deal with that. A is a member of the set of X, which is a member of the power set of N, such that X, the cardinality of X of the the component, is it? I'm losing my train of thought. I think it's a component. Yeah, that's what I call it, the component. Okay, so I just some of my logic here. To go back. Okay, it's a component or whatever. Yeah. Okay, that's going to be a long sentence, but let's try it again. Less than infinity. This is going to be a hard one just because it's complicated, but maybe it's not that complicated. Okay. A is a member of the set of all x's that are the set of the power set of the naturals, such that the component x is less than infinity. The cardinality of component of x is less than infinity. So, what are they even trying to say here? But maybe that's the whole point. Maybe they just want us to say, we can say not P. Simply take the statement, change it up and make it greater than. Okay, I guess it wouldn't make sense that way. A is a member of the set of X, which is the set of the power sets of the naturals. We just have to make the statement, and I want to know how we're gonna package this, or we just call it P, the whole statement, such that I guess such that can probably be. Hang on a minute. Let's try. I want to try P and Q. But A is a member of the set. That's the statement. What goes on inside that statement? It's like saying A is a member of Q, which is a little different. They're not on the same level. This is a hard one. How do you want? There's probably. I think they intentionally made it a little complicated. They don't want us to necessarily unpackage the whole thing. I'm gonna go with the not P. Okay. P, and we're going to define this in a way that is not a member. Yeah, because the double negative gives us a positive. I want to try that. It's probably wrong, but we're going to find out. Yeah, it's wrong. Again, it's not necessarily wrong. It's just not the answer they're looking for. Should probably put it that way. What they want. Let me take out what I wrote here. Okay, it's going to take some unpackaging. All right. But it's not too terrible here. So here we go. A is a subset of the natural set, and the cardinality of the component of A is less than infinity. Okay, so the second part's easy. We can see that right there. So if we take A as a subset of X, essentially, notice what they did. A takes the form of X, sort of. So yeah, the A gets, as I'm reading, okay, this could be a wrong explanation, by the way. Logic is kind of a hard thing to work your way through. Like, my explanation might be correct or it might be tenuous. Just keep that in mind. But as I read it here, A becomes a subset. And because A contains the power set of N, and A contains the sets of it's a subset. So this plus this makes it a subset, essentially. It is a subset of the power set of the naturals. So now why it doesn't say it's a subset of the power set of the naturals, I'm not sure. But let's just say, I guess, that the top, which is true the most basic thing is A is a subset of the natural set. And the cardinality of the absolute value of the cardinality of A is less than infinity. So remember the component of A. The component of A is that, like, let's say if A is 1, the component of A would be from 2 to, say, infinity minus 1. Something like that. Although infinity minus 1 is still infinity. So it's kind of hard to wrap your mind around, because it's hard to say less than, what does even less than infinity means. I know that means it's a terminating set, but whatever. It's not bad. Like, in terms of a brain teaser, it's certainly a good question. Okay, let's go to 13. And I am losing my voice here. Okay. I didn't know it was by Orwell, by the way. Okay. 1984 and Animal Farm are my two favorite works of his. By the way, a fun fact: 1984 was meant to be about 1948, and essentially it's the totalitarianism. The idea was that there was governments were much stronger, more totalitarian than they are now. Although I guess it's debatable in a sense, but you can get canceled just like for being part of the Communist Party back then, which, again, both countries were ready to nuke each other. But yeah, and that, like, you look at the McCarthy hearings. Although the McCarthy, I think it was in the 50s. I think it was 48. I gotta look it up. And the other thing is Animal Farm. Napoleon is basically Stalin. The whole thing, it talks, essentially, it deals with the proletariat, the Russian peasants, how they were just essentially bamboozled by the communists. It's a great book, and it's a lot of truth to it. But Animal Farm, it's like a kid's book, but it's like telling the story of the Soviet Union, but for kids. Great book, by the way. Oh yeah. Anyway, getting back to the truth tables here. All right. Human beings want to be good. So that's the main point. Not too good. Let's see here. Q. We have two knots. Can we put them separately? We can go PQR, I guess. We can say let's think about this for a minute. Human beings want, this is getting more into what proofs are going to be like. We're going to stare at something for a while and try to figure it out. It's not going to be like super fast. Oh, we're going to get these proofs. Remember, I don't have prepared notes. I do this on the fly. I'm learning so that I can retake this class. So yeah. Okay. Human beings want to be good. I want to reduce this just to 2 points. Human beings want to be good all the time. Human beings want to be too good. Okay, So those are two negatives, right? And then I can go not P and not Q. We can do that. Human beings want to be, let's try that. I'll make that P. So we're gonna not this. In Q, human beings want to be good all the time. Okay, now I'm going to move this a little bit more over. I got a bit more room. Okay, let's try not this. I'm going to say not P and not Q. That's how I see it. So if we say not human beings want to be too good, so they don't want to be too good, and not human beings want to be good all the time. So they don't want to be good all the time, and they don't want to be too good. So that, at least logically, makes sense. Even if I don't get this right, I would at least get partial credit for this. That's how I feel about it. Let's see here. Oh, they went PQR. Okay, yeah. I wanted to do that, actually. You know what? I'm not going to start it. Let's try PQR. And in that case, let's just see if I could lower this a little bit. Okay, because the problem is they said of the form P and Q, P or Q and not P. They didn't say we can use R, but yeah, I guess in a sense we can use R, and that's fine. R. So we're gonna assign that to want to be good. A minute. We're going to just drop this down here. And then okay. Get that. Okay. Human beings want to be good. Okay, so now we're going to say P and not Q. And now I didn't stare at the answer. I can get this wrong. Keep that in mind. Not R. All right. P. Human beings want to be good. And human beings want to be too good, not. And human beings want to be good all the time, not. This is like the not joke from Borat. Anyway, so yeah, that's another way how to do that. Let's see what they say. P and not Q and not R. Human beings want to be good for P. Q. Human beings want to be too good. Yes. R. Human beings want to be good all the time. Now, it feels like, like I wrote word for word, which I did, but not because I looked at their answer. It's just because the logical structure of it made sense. And essentially, you took the sentence and then you formulated it in such a way that you have to negate it. And just, this isn't like, I mean, we could have written more flourishly, I guess, but essentially in a more straightforward way is, if human beings want to be good, or not too good, we just say they want to be too good, right? The not is right there in the sentence. The not is right here, so we change that to a positive. And then we're going to say, we take out the not, and we put it here. We take out the not, and we put it here. How cool is that? That's the simplest explanation. And then I take the beginning. Human beings want to be too good. Human beings want to be too good. Well, human beings want to be good all the time. The nots, I just pulled them out and then kept the first statement. So there we go. And the reason why I repeat human beings 3 times is just because that the structure of it, if you just say Q want to be too good, who? What is it that you're saying? You know, you have to be very precise with logic. There's no room for just like ambiguity, right? You know, if you just write something like that, that's an ambiguous statement, and that's a problem, and that wouldn't work. Okay, so that completes this chapter. I hope you had fun. So starting with 2.3, I will again read the chapter before we get into the questions. Each chapter is only like 2 pages, 3 pages long. Yeah, it's dense, but it's going to be like this going forward, and it's only going to get more dense. So get ready for it. All right. Well, I hope you enjoyed this stream. Have a good night.